So let's start. So good afternoon, everyone. My name is Carlos Quesada. I am an associate researcher at the University of Deusto in the city of Bilbao, in Spain. My work is carried out within the framework of the European Horizon 2020 research project named Y. And the session today is entitled High Resolution Time Series Processing. I have to say that we are pleased with the wonderful reception that this workshop has had, judging by the number of attendees registered. Let's see if they all come here. And we hope you find it useful. So the idea of this workshop is that we can follow step by step the process that we have followed in the framework of the Y project to analyze our time series. These time series are load profiles, that is electricity consumption values over time of different households. And these load profiles have durations of several years and resolutions of 1 hour. This session is divided into two parts. In the first part, which will take around 70 minutes, we will follow the Google Colab presentation that allows us to run and modify the code in the R programming language for the different steps of our analysis that I think that you all can see in the shared screen that I'm showing. In principle, all of you have already received an email with the link to this Google Colab session. And in case you don't have a Google account, you have also been sent an address to a Jupyter notebook so that you can also follow the session from there. And if not, in case you need it, one of the co-chairs will post the links here in the chat. And in case you have neither Google account nor Jupyter at hand, you can always watch this session, learn with us. In the second part, I will give way to my colleague Leire, who will explain the steps that we have been followed, or that we have been following to develop a taxonomy from the results that we have obtained here. So the first thing that we can do, I imagine that you are opening, you have opened that session of the Google Colab that you can participate. So the first thing to do is, if you haven't opened it, just open it right now. And just before starting, let's install some packages. And this is done just by clicking that play button here. It takes an estimated time of around 5 minutes. So while this is being installed, I will do I will review some concepts of data science and machine learning. And to do so, I always find quite interesting to show infographics that I found on the internet. For example, this one is by the Data Prof on Twitter. And it explains the data science process in 5 steps, as it is depicted here. So in the first step, it's data collection. This is the process of gathering the data and measuring information on the targeted variables within an established system. The second step is the data cleaning, which is the process of detecting and correcting or even removing the corrupt or inaccurate records from a table or a data set. The third step would be an exploratory data analysis, which is an approach for analyzing data sets to summarize their main characteristics using, for example, statistical graphics or any other kind of data visualization methods. The fourth step would be model building, in which we use machine learning models that are built by first learning and generalizing from the data, and then by applying the acquired knowledge to the new data to achieve our objectives. So it's important to remark at this point that without data, we cannot construct any or build any kind of model. And the last step would be the model deployment, which is the method by which a machine learning model is integrated into an existing environment to make practical decisions based on data. So the contents of this session, as you can see in the table of contents on the left here, is organized more or less according to this scheme. The author of this infographic has also included some bars indicating how those 5 processes are related to the different areas of knowledge. We see, for example, that the areas of data engineering, data analysis, or machine learning engineering are related to particular parts of this process, while data science is covering the whole process. So now that we have mentioned model building and machine learning, let's look at this in more detail. Here, a different author, I have taken this image from Kaggle, as you can see here, provide us with some information about the different classical machine learning algorithms that we can find and their taxonomy. So here, as you can see, is a tree with two main branches, one for supervised algorithms and the other for unsupervised algorithms. Supervised algorithms, on the one hand, are those that require our data to be labeled in some way. From this labeled data, both classification and regression algorithms can be applied, which are mainly focused on predicting values. And unsupervised algorithms, on the other hand, are those in which our data are not labeled. The main algorithms used in this branch are clustering algorithms, which are the ones that we are going to use in this session with the data that we are going to get. Also dimensionality reduction algorithms, and those algorithms that allows us to make data associations. Okay, so just to finish that part of introduction, just a few words to explain a little of the work that we have done in the framework of the Y project that we are going to replicate in this session today with this collaborative web page, let's say. So first, notebook, let's say. First, we have a large set of thousands of dwellings, each one generating a load profile, which represents the energy demand over time. And there are differences between load profiles that are due to a lot of factors, such as, for example, the size and type of the dwellings, the socioeconomic conditions of the people living inside, their consumption habits, and so on. So those load profiles are made up of hundreds of thousands of samples, and they may have different lengths and start and finish at different times. Due to this, it's necessary to find a way to work with them in an efficient way. And this is performed by feature extraction. Feature extraction is a dimensionality reduction technique that computes a set of values, as you can see here, from each load profile. These features represent certain characteristics of the load profiles, and by reducing the load profiles to a small set of relevant features, all the analysis that we perform after that will be facilitated. So finally, by applying some unsupervised classification techniques to the features, we build the set of profiles of the electrical profiles that we are looking for. So the objective is, from the load profiles, obtain a segmentation by their electrical behavior. Okay, so we are going to see how we have deployed all those processes in this session, and let's see. So the first thing is going to see if all the things have been installed. We see that yes, it has taken just a bit more than 5 minutes to be installed, but okay, we have all those packages installed, so we can go with the first point in our session, which is the data collection. So indeed, in that part of the presentation, what we will do will be retrieving a data set of load profiles from our repository. That repository is a shared folder that we have on Google Drive. If you click here, you can see that folder. But what we are going to do is in this code cell here, what we are going to do is creating a local folder named content data. We can see the folders that you have in your local part of the virtual computer that we are using. So we will create a folder named data, and we will download all the files from that shared folder to that folder here. So we click the play button, and we can see in a few moments how the files are being downloaded from that repository, and they will appear here in that folder. So they are being loaded. So we can check, for example, that they are CSV files, which contain comma-separated values. Now we will see them. And those files have been provided by Goyener, which is an energy retailer, and contains data from electricity supply points identified as households in the northern of Spain. So now that we have loaded all our files, we can inspect what is inside of those files. And by clicking play in that code cell, we can, what we are doing, first of all, is putting the contents of all those files inside a list. So we are loading each one of the files as a data frame, and we are putting that data frame in an element of a list in R, so that we can work with them throughout all the session. So now that we have that list with all our data loaded on it, we can access to the load profiles just by indexing that data list. So in the following code, we can see the contents of, for example, the element 12 that contains the file number 12. So we click play and we see the kind of things that this file contains. So we are seeing the data frame, and we see that it contains, well, we have printed just the header, let's say, on the bottom part of the file. And we see that it contains timestamp values, where the first column contains just the times, and the second column contains the values of the energy consumption, of the consumption of the energy, of the electricity in kilowatts hour. Okay, so let's visualize this kind of data, which is always better than reading numbers. So in that part of our session, what we will do will be become a bit more familiar with that data that we have put in our list. So what we are going to do is plotting the load profiles so that we can check that they look like the time series. We will spot some gaps of the missing values. We will visualize the load profiles as heat maps. Okay. So the following code cell plots a complete load profile. So for example, now we are going to plot the load profile number 10 by clicking on play. I recommend you that you follow also the same steps that I am following. By clicking on play, it takes just 2 seconds to plot the complete load profile contained in the file name 10. Okay, so we see that load profile. Well, we see a lot of information here. We see that, for example, data goes from mid 2017 to late 2020. We see also that there are some peak consumptions here, which have reached almost 3 kilowatts hour on a couple of occasions, as we can see here. And we see that every year the consumption, the electricity consumption, drops in August. We can see this. This indicates for sure, since we are talking about load profiles from households, that families living here are taking some kind of summer holidays. So you can modify the code. For example, if you want to see the file number 21, for example, or whichever you want, you can see it here. So we can see that load profiles have different aspects. You can see that each one of them looks different. So you can play with this, I mean, just by looking at this. So probably showing that the whole file is not the best way to inspect a time series. So in the next code cell, what we are going to see is inspect the load profiles in detail for particular time intervals. For example, in this case, we are going to inspect file number 1 from November 18, 2019 to November 21, 2019. These are 4 days, I think, and we can see those 4 days here. We have chosen to be plotted as a series of lines and points, and we see the behavior of with more detail. In more detail, we see, for example, that consumption is higher in the late evenings and also around midnight. And we also, if we pay attention to this here, we have found a gap of data which is missing. So we see that here there are some circles indicating samples which are not present here. So this is a gap that must be corrected. So we will see how to correct these kind of gaps later on. So now it's also interesting to represent the data using heat maps. So a heat map is a visualization technique that shows the magnitude of a phenomenon as a color in 2 dimensions. So in this case, the magnitude that we want to show is the consumption in kilowatts hour, and the 2 dimensions that we are going to show are in the x-axis the days of the year, and in the y-axis the hours of the day. So this code here, this for showing the heat maps, I have divided the code into two code cells. So this code cell here, what it's doing is arranging the load profiles to be displayed as a heat map. If you understand our code, you can read that we have been working with the library load date, which is playing a bit with dates. By playing it, we are loading that function into our environment. And by clicking the following one.
Sorry, Carlos,
yes.
Your mic, there's something I think wrong with the mic because I can't hear you properly anymore. I don't know if the others have the same problem.
Sorry?
I can't hear you very clearly anymore.
Can you hear me? Does anyone have any other problems with hearing me?
Yes, Carlos, you start sounding quite funny. It's like you are far away.
Oh, really? Now? Do I have to get closer to the mic, probably?
Yes, now better.
Now better. So I was too far from the mic. Sorry. Okay, I will try to talk this length. So thank you very much for telling me this kind of thing. So what I was saying, I don't know if you have followed me, is that we are going to show the data as heat maps, okay? So we have loaded that function into our environment, and we have now to we have to load this function into our environment by clicking also the play button. So this piece of code, what it's doing is taking the output of the previous function and rearranging all the values so that they can be plotted or displayed as a heat map. So this is the function that is calling those 2 functions. It is a for loop which will load and display all the values, all the data sets as heat maps. So if we click, we see that we are seeing. Let me check. Let me move it here. Okay. So here we see that we are obtaining, or we are displaying the contents of our data set as different feedbacks, one per each one of the files that we have here. So this is a way of representing, you can see in a glance, the behavior of a household for a complete year during the complete days. Okay. So
Carlos,
really, yes. See,
you continue to sound quite far away. I don't know if you have moved the microphone or if have been switched.
I mean, in principle, the microphone is the one which comes by default with the laptop. So I really don't have any.
Now
other...
you sound quite better. So I don't know if you have.
I mean, I really don't know what could be the problem. So let me mute myself and okay, now?
Better.
Better?
Yes.
Okay, so, okay. So I hope there's no a huge problem. So what we see here is that, as I was saying, that we can see the electricity consumption of the different households. We can see how they behave. We see, for example, yeah, that household shows some consumption between 2 and 3, and that those consumptions are variable. Here we see in all of them some steps, some shifts that are provoked by the summer time, by the daylight saving time that we will have to correct, and we will see how to correct this. We will see interesting consumptions like this, which are driven by the darkness, let's say. And this is the more or less the aspect that all our data set has. Okay, so as you see, the redder the consumption is, more energy they are consumed. So as you have already done, you have paid attention to the different consumption types. So the following step that we are going to follow, if we go to here to the data of contents, is the data cleaning. So the objective in this part is to make the data usable for constructing our model later. So what we will do, there are 3 things. We will do the imputation of the missing samples, as we saw that there are some data sets, some load profiles that have missing samples. We have to correct this. Then we will do an extension of the short time series of the short load profiles, because we need at least 2 years of the consumption to compute the features that we will do later on, and we will see why. And we have also to correct the daylight saving time issues, such as those shifts that we see here. So first, the imputation of missing samples. Imputation, as you already know, is the process of replacing the missing data with variables that substitute them or that replace them. To impute the values, what we are going to use is the package impute TS that we have already preload before in the beginning. So to use that function for imputing the samples, we have to first convert all the values that are missing as NA, as not available. Then this function will allow us to impute by using different algorithms, between which or amongst which we can find interpolation, the last observation carried forward, but there are also, for example, algorithms based on the mean, and also on random and Kalman filters. There are many. That function in that package contains a lot of algorithms. So
again,
yes, again,
yes.
So, but I don't know how to solve this, because I don't know which is the problem.
It's that you need to be clear, talking clearly to the microphone in front of you. I mean, try to not look
Not to move the head.
too much. Yeah.
Okay, so if I talk like this, can you hear me well?
Yes, perfect.
Okay, so I won't move my head. I try to do it. Okay, so as I was saying, we will use the function NAC split from the impute.ts package, and we will consider because since we are going to do the imputation using the interpolation and the last observation carried forward functions, we are going to consider one seasonality of the load profiles. Remember that when we are working with load profiles, they have three kinds of seasonalities: the daily seasonality, the weekly seasonality, and the yearly seasonality. So we are just working with the weekly seasonality. So the solution that we have adopted to impute is if we found a gap of missing values, which is small, and by small we mean up to 8 hours, we will be using the interpolation algorithm. We will be using interpolation techniques to complete or to give a value to all those missing samples. Instead, if the gaps of missing samples that we found are large, and with large we mean more than 8 hours, we will be using the last observation carried forward technique, taking the data from the previous week. So we will just go to the previous week, we will copy the data, and we will paste it. So the function in charge of doing this, of completing the missing samples with NI values, is this one. By doing this, and by calling this function with our data list, all the missing values will be changed or turned into NA, which means not available, and we can check it visually by clicking here. So now it's displaying the same file that we had above, and we see that all that gap of missing values now they have NA values, which are interpreted by this plot by something which is empty here. So now we can have a real awareness that we have a gap here. So the following step is using the impute data frame function here, which is in the next code cell here, and we will use it to impute the missing values of our load profiles. So it will be doing the same solution. I mean, it will be doing the solution that we have suggested here. So the first thing that we have to do is to load that function here, and finally imputing the files by clicking here. So by doing this, all the missing gaps will be replaced by the values provided by the last observation carried forward, if they are big ones, or by interpolation algorithms if they are small. So we can visually check, well, the function offers an output argument in which you can see which have been those files that have been imputed. In that case, for example, we see that the file number 1 has been imputed, and then we can visually check how those missing samples have been replaced. So by clicking here, we are saying that we want to print in red all the samples that have been replaced or imputed. So we see here, I have plotted just one complete week so that we can see that that part here corresponds to that part here. So we are doing this.
Carlos,
Yes,
again,
I don't know what to do.
now you sound better.
Yeah, but I mean, I don't know if this is something that happens and then disappears, or I don't know. Let me check, because I mean, because it says, let me try now. Can you hear?
Now better.
Now it's better. Maybe by default it was using several microphones or something like this. It was using a technology, Intel Smart Sound, something like this, that is not working properly. So can you hear me right now?
Yes.
And even if I go far?
No.
No. Okay, here. Okay, so let's continue here. Okay, so as I was saying, can you hear me right now? No?
Yes.
Can you hear me? Okay, so as I was saying, seasonality is important because we want to respect the values. For example, we are aware that, for example, during the weekends, the behavior is different than during the work days. So we have to respect that seasonality, and that's why we are taking data for imputing from the previous week, okay? To respect that seasonality. So now that we have our missing data imputed, the next step would be to perform an extension of the short time series or the short load profiles. So for the feature extraction analysis that we want to perform, all the load profiles must have a minimum length of 800 days. And why those 800 days? 800 days are more or less 2 years. They are 2 years and more or less 2 months, which is the margin that we provide. And we are really interested in those 2 years. I mean, why? Because when we will compute features for all those time series, we require to capture, let's say, the year seasonality. And the year seasonality is only captured if we have a time series longer than 2 years. So that's why we are going to extend all those time series which are less than 800 days. And how are we going to do this? So load profiles that are longer than 800 days, they don't require any kind of extension, so they are already okay. Then time series that are shorter than 1 year will be discarded because we cannot replicate something which is shorter than 1 year. And all those files or load profiles which are greater than 1 year but less than 800 days, we will replicate them by using the same function that we have seen before. But instead of using 1 week for applying the last observation carried forward, we will apply 1 year. In particular, it's not exactly 1 year, because since we want to respect, as we have already said, also the weekly seasonality, we see that if we go backwards in time, 365 days, if we were in a Friday, we will be in a Thursday. So we are looking for that coincidence of the day of the week. So instead of subtracting or going the 365 days to the past, we will go 364 days so that it coincides with the same day of the week, and therefore we will respect the weekly seasonality. Okay. So as it's written here, all the load profiles with at least 364 days can be extended up to the 800 days by replicating the content the times it's necessary. And the last observation carried forward will be applied by using the same impute TS package that we have used before. So here we have created a function to extend those load profiles that require the extension. It's a long function, but it's well explained here. I mean, you can follow the comments. In general, all the functions that I have provided are well explained with the comments here. So I'm not going too deep into the functions because, I mean, it will require time how to explain the way I have created those functions. But here you can see, for example, that there's a part in which it's checking the days that they are required, and then there's another part in which they are in which that function is imputing those values. So we load that function into the environment by clicking it's already performed, and the load profiles are finally extended in case they need it by applying this function. This function is calling that extend imputed data frame function that we have seen before, and it will display the results as we have done with the imputed values. So it will take a few moments, I think. Those functions don't used to take too long. So here, as we have seen, it has been required to extend those 5 files that we see here. And we also see that no load profile has been excluded for being shorter than 364 days. Just to recall that if they were shorter than that year, they should be excluded. So let's do some visual check of those extensions. For example, if we want to check the aspect of the newly extended file 11, we can click here, and we will see the extension in green. As we have already seen, well, what we have already here, we are showing that the extensions are bound to the beginning of the time series. It could have also be bound to the end, but we have decided to bound it to the beginning. Just, I mean, arbitrarily. There's no way to decide. I mean, at the end, the result that we are going to obtain is going to be the same. So we see that the newly created data has been extracted from the subsequent year here. So this part of the time series, this part in particular, has been copied and pasted using that function. If we want to check a different file, for example, file 24, I mean, whichever of the files that you decide. For example, this one is a strange one. Okay, it has a weird shape, but we can go with a different one. For example, 26. Okay, we see that they have been copied and pasted. Probably the interface between the copy is not as good as we expect, but in general, the behavior is kept. So just to finish, just to check another one. This one. So we see that sometimes the copy is quite good. Okay. So the last thing to do in that part of data cleaning is to correct the daylight saving time. That as we saw before, it's producing some shifts at some times that are just preventing us to see the correct behavior in the local time. Okay, so as we explained here, the hourly values of the load profiles in the data set that we have already loaded are not adapted to see the changes produced by the daylight saving time. So if you don't know what the daylight saving time is just that implementation of forwarding by 1 hour the clocks in spring and setting them back 1 hour in autumn to return to the standard time. This is done to save some energy, or they say so. So we are going to see just one example. For example, before doing the correction, here we have the time series number 10. We see that shift produced by the daylight saving time, one in March and another in October. And we want to correct that. We want to put it so that we can follow the local time. So to do this, we have created the function correct DST, which is correcting that shift. So what is doing this file is taking the data set, or it's taking the data frame of the load profile, and then it's padding with extra rows when it's needed. It depends on if the load profile starts in summertime or not. So it has to check several things. And then the same way as they are adding extra hours, they have to remove them when it's necessary. So by loading that file into our environment, we can now execute it. So by clicking here, we are applying the correction to all our load profiles. So we click here. It has taken 2 seconds. All the problems with the summertime has been corrected. And just to check again, we can check if the file number 10 has been aligned to local time. We click and we see that our load profile has been corrected. Now we see that all the values of consumption are being generated in local time, and all the consumption is produced as if the daylight saving time didn't exist. Okay, so with this we have complete our part of the data cleaning. We have performed the imputation, the extension, and then the correction of daylight saving time. And now the following step is to do the feature extraction. So the objective in this section is to compute a series of features from load profiles. So as I explained at the beginning in the introduction, the feature extraction is a dimensionality reduction technique that allows you to compute a set of values from each load profile. So those features represent certain characteristics of the load profiles, and reducing the load profiles to a set of features is really nice because it allows you to analyze them regardless if the length of the load profiles, or if they start or end at different dates. And it's always better to have those values to compare those load profiles. So to extract the features, we are going to use the package called TS features. We have to load it by clicking that button here. It has been fast. We are also loading the library forecast, which is already needed. So to compute features using that function here, it requires that the input objects are of the type TS, that is time series. So all our list of data frames have to be converted to a list of time series so that we can work with it. So the following function is converting all the data frames into time series. Here we load the function to the environment, and then we create that list of time series. They have been already created. So if you want to have an idea of how a time series looks like, here you can see it. So it is just a series of numbers with no timestamps, because all the data preferring the time has been converted or coded as integers here. So here you have an indication of a series of integers with represent the time. Okay. Here we are also containing the different seasonalities, the daily seasonality, the weekly, and the yearly. Okay. Okay. So now what we are going to do is using the TS features function to compute the features that comes by default with the package for all or for our new list of time series. So the default features that the function TS features compute include values such as, for example, entropies, measures of trend and seasonality, autocorrelation coefficients, several different features that you can get more information if you click here. You will go to the paper of the TS features function, in which it explains which are the features that are being computed, and you can get more information there. So by default, we are going to compute the features. The estimated time for computing the features is 10 seconds for our for our recently created list of time series. So here we have it, 10 seconds. And we are going to do right now, just to have an idea of how the features look like, is printing printing the variable fits, which contains a table, I think, of our computed features. So here we see the name of the feature computed, for example, the trend, spike, the linearity, the curves. As you see, one feature is just one value, and each one of the columns is one feature, and each one of the rows is one of our load profiles. So we have computed 23 features, or not 28 features for each one of our load profiles. So if we just to do some trial, plot one column of these features against the other, we will see in some cases, that the points that we have plot tend to group together to form clusters. Probably those clusters that we plot are formed by load profiles with similar characteristics. So this fact is what gives rise to the idea that clustering load profiles based on their characteristics or their features can be interesting for grouping them, or for grouping them by similar characteristics. So in that case, we can do the trial and plot those two, so the columns 12 against the column 23, which contains the daily strength and the weekly strength. Okay, 13. And we can plot to see what happens. So, okay, we see a cloud of points, and we see other points that are far. Probably those 2 points are one cluster, probably those are other. This is just a visual example that by plotting some features, they can be clustered in somehow. However, we are not interested in these default features, because we think that those default features are not as good as we expected to doing this clustering. This clustering, that this is a very, very basic clustering, just by plotting, just by contrasting two of the features. I mean, this is just to see that you can get some cloud of points. If you change the different columns, for example, you plot 12 against 18, or I don't know, any of them. 19, for example, you will see another different pattern, and who knows what is trying to be plotted here. So, as I said, we are not interested in the default features. We are going to create our function to compute the features, and we are interested in what we have called seasonal aggregates. Seasonal aggregates are features that are obtained by splitting the time series into subsets and then computing statistics from each of those splits, of those subsets. For example, the mean and the standard deviation. We have defined 8 different groups of subsets, with each subset corresponding to a particular time band. Okay, the subset comprises all the values of the time series for which their date and time fall within its time band. So we have defined, as I said, 8 different groups, which are consecutive intervals of 1, 4, and 6 hours, days of the week, for example, all Mondays, all Tuesdays, all Wednesdays, weekdays and weekends, all the months, sorry, all the seasons, and combinations of groups of 4 hours and seasons. Okay, so to compute those seasonal aggregates, we require 5 long functions that I will explain a bit here, and we will load it to our environment, and we will see what happens. So the first of the functions is this one, get extrema dates from time series, which is getting dates from the time series that we have already seen that they are dateless. They don't contain any information of the date, and we have to extract that information of date from those time series. The second function is get bins that will we will get the time bands from the time series. The third function that we are going to load to our environment is the get seasonal features from time series, which is computing the seasonal aggregates using the time bands. This is the function that is doing the hard work. Then the other function, which is generating the names of the features, because we need the features to be named somehow, and this is the function that generates the names. And the main function that calls the rest, which is the stat data aggregates, and that we will use to pass to the function TS features, so that the features could be computed. So we load the functions in our environment. You can see, for example, here we are getting the bands. Here we are dividing our time series into hours, into days. We are doing those aggregations here. Here we are computing the means and the standard deviations of all those values in those bands. Here is for getting the names of the features, okay? And here is the function that we will call using the TS features function. So we will do the play. And now that we have loaded all those functions, we can compute the seasonal aggregates. So the expected time for computing this is 1 minute. It's now computing the files. And when we compute those features, which are the seasonal aggregates, we will have a look at the table, or at the data frame, which is really a table that we obtain, so that you can see. So you will get an idea of what kind of features we are computing. But okay, just we will have to wait. So as I said, the interesting function is this one. This function is getting the bins, let's say the different different bins of time, and it's computing the values the means and the standard deviations, and it's aggregating. It's using the function aggregate from the stats library, which is aggregating all the data in all those time paths. Okay, so let's see. I think
So can I ask a question? So it basically
yes, of course.
just for each house, it calculates what's the average during the 4-hour period, during a week, during a day, during certain hours. That's the idea, and you're calculating the average and the standard deviation for each household.
Yeah, I mean, for each one of the load profiles of the households, for each one, we are separating those load profiles by time pins. For example, from 12 to 4, from 4 to 8, from 8 to 12. And we are computing the mean inside those bins for all the load profile, okay? For the complete load profile. So this will give us a value, a mean value, and a standard deviation value, and we will use them to do our clustering later. Okay. So I don't know if it's clear how the division of time, but I mean, we are computing the mean for those groups. For example, when we write here 1 hour, we say that we take, for example, all the 11 a.m. of all the time series, we compute the mean at that time, at 11 a.m. And this is one feature. For all the 12 a.m., we compute the mean and we obtain that feature. I don't know if it's clear.
And then, so hour 1 will return us 24. Will it give us then a series which is 24 hours? So one.
This is the mean energy. This is the mean energy for this period of time, a particular period, which is, for example, in that case, for 1 hour, for 11 hours, 12 hours, 14. We also have divided it.
Okay, so hour 1 is basically 11 a.m.
Yes, in that part here. If we are talking about groups of 4 hours, we are talking about from 12 to 4, from 4 to 12. If we are talking about groups of 6 hours, we are talking from 6 to 12, from 12 to 6. If we are talking about days, we are talking on Mondays, on Tuesdays.
Let's talk about days. So then it basically then gives us a value, which is the average consumption.
The average consumption on Mondays.
Wednesday.
That's the thing. Yes.
Wednesday, so it's like 7 days of the week.
Yes. Yes.
For each.
Yes, that's exactly what we do. And we also have those nice combined periods, which are groups of 4 hours and season, which will be the ones that we will use later. Let's go to see it, because I think that we will finish. So here we can see what we have computed. So it has created a lot of different features, because, I mean, we have computed not only the value of the energy, but also the relative value as a percentage. This is indicated by rel, the relative, by absolute. So we are computing, so the mean energy at the hour 0, or the mean energy at the hour 1, the mean energy at the hour 2, and so on, till we have the last ones. For example, the mean energy in the group from 8 to 12 in winter, which would belong to the last bin that we have shown here. Okay, so now that we have all those features computed, we are doing the segmentation. The objective is clustering those load profiles. The clustering consists in grouping the sets of objects that looks that they are similar in the same group. And we have used the package CL-valid, which is used for clustering and for computing validation results. That package is really complete. It contains several clustering algorithms, such as hierarchical algorithms, partitional algorithms like k-means, unsupervised neural networks like the algorithm SOM with self-organizing maps, the fuzzy algorithm Fanny, and any other kinds of algorithms. So we are loading the libraries, and we are going to set the random seed, because there are some algorithms that are using random numbers, and we don't want those numbers to be different each time that we execute the code. And we have decided to select a series of features to perform this clustering. And in particular, we are using all those features computed in the eighth group, which are groups of 4 hours and season. For example, we are saying that we want to be clustered by the values. For example, in the values computed using the mean from 0 to 4 in spring, the mean from 4 to 8 in spring, and so on till the mean from 8 to 12 in winter. Okay, so all the combinations, all the different combinations in a year. And we have also included the mean during weekdays, okay, which is the mean value of energy that we obtain from Monday to Friday. Okay, by combining all these features, okay, we are going to establish that variable here. So what we are going to do now is to call the function CL-valid, which will perform the clustering. It will provide a lot of, well, you have to pass some input arguments, such as, for example, the object, which is our data frame of features, the number of clusters that we want to be computed, which in that case, we have decided to compute from 2 to 10 clusters, just to see what happens. The CL methods input variable, which asks you for the different algorithms that you want to use. In that case, the hierarchical and the k-means and SOM are going to be computed. And also the different validation measures that will allows us to have a hint of which is the correct number of clusters that we need, or that are the best option to be chosen. So we are now computing the clusters and the validation measures. It will take just 8 seconds. It has been fast. And we obtain a huge object that brings together all the results. We can see it here. We can see that it's a really, really huge object with a lot of information. It contains information of all the clusters performed using all the different methods that we have asked to do, and with all the different validation measures. And just by going to the interesting data, for example, if we go, let's go to see what are the interesting values. So it is possible now, just by getting, for example, what we are going to do is going to see how the clustering has been performed when we have chosen 4 clusters, and we are going to see the results for each one of the clustering methods that we have selected. So for doing this, we are going to plot the mean cluster. So once that we have obtained the clusters, we are going to represent as a heat map the mean value of the time series of that cluster to see what's inside. This is done by this function that we have to load into the environment. And now let's see what we obtain for each different clustering method. So let's start. Let's see what happens with the hierarchical clustering using just 4 clusters. So here we have to call that huge object this way by using the function cat3 because we are working with hierarchical clustering. So we see that the hierarchical clustering has labeled almost every time series as being in the cluster number 1, which is not providing much information because I mean, if you are putting all the time series in the same cluster, probably you are not clustering so well. So we can plot the clusters that we have obtained, and we see, okay, that is generating one cluster in which the 73% of the elements are here. So the second cluster looks like this, which is very similar to the fourth cluster. Then we see that it has created a cluster here that would be legit. But since those two clusters are more similar, probably this clustering is not being so good. So this is what I have written here. So let's see what happens with k-means.
Carlos,
yes?
Speed up a little bit.
Yes, I'm finishing. So let's see what's happening with the k-means clustering. We do the same. I mean, with the k-means parameters by default, we obtain more or less the similar clustering as the hierarchical. So it is indicating, because I mean, this cluster
Carlos?
is quite similar. Yes?
Can you take one of these cluster graphs and explain what do they actually say? Because I'm
What's the meaning of this? Okay, so I will explain it with the following, which is the one that it's working. We will see what's the result of the self-organizing maps. We see that it has created some clusters containing different values, containing different time series per cluster. And if we plot, we see that it has created some interesting clusters. For example, here, we see here that half of the time series belong to that cluster, which indicates that people is having more consumption during the lunchtime and also at night. So these people that wakes up at 8 in the morning and goes at bed at 12, because during the night there's no consumption, and in summer the consumption is a bit lower. So there's another group here in which we see that they are having consumption during the mornings, but not during the evenings. And again, they have consumption in the night, at night, or at the late evening, let's say, indicating that, for example, these people here in those households are working outside and they are not living at home. So those profiles here are indicating that they may be, for example, late lighting, for example, house lighting or something like this. I mean, there are not many node profiles like this, but this is just for generating that example here. And this is just energy driven by light, by darkness, let's say. When it's dark, the consumption starts, and it's following the solar patterns. And finally, we have another pattern here that is explained because, I mean, they have consumption in summer. During the weekends, we see that those stripes indicate the weekends, and also during holidays, which indicates that they may be secondary residences or the houses that you go when it's summer or when it's weekend. So we see that the song is doing an excellent performance because it's obtaining patterns that we can understand and we can see feasible, and that they represent some things that may be applied to the reality. And then the last part that I wanted to show is just the quantitative. I will be very fast. The quantitative assessment, which is just by using the values of the validation measurements of the CL-valid package, which is computing some measures for getting an idea of the number of clusters that we have to use to compute our clustering. So there are 7 different validation measures inside that package, but we are going just to see what happens when we show the silhouette width, which is the one which is more known, I mean, let's say. So if we represent the silhouette width, which is a measure for the different values of the packages, we may have an idea, for example, using the hierarchical and the k-means are quite similar. They are indicating that, I mean, there's a huge, I mean, we have to take the maximum value, but I mean, we have to be a bit cautious with this kind of rules for deciding the clusters. We see that there's a huge fall of the value here, indicating that probably this is the most interesting value, which corresponds to 4 clusters. We see, for example, that this value hasn't been possible to be computed for some completely, and it's indicating that the best value is 3 clusters. I mean, the idea that we have to get with this is that the cluster validation measures are just support tools for taking decisions with on the most appropriate number of clusters, but they don't have the final say. So the number of clusters is usually decided on the basis of expert knowledge. We are going to see in the next step, which is my colleague Leire, who is going to explain how that result assessment has been obtained by creating a taxonomy of the obtained results. And she's going also to talk about the knowledge extraction, which is the creation of the household persona behind each one of the obtained clusters. So Leire, I give you the floor. The floor is yours. So
wait a little bit. It's already understood the question that was made before.
Yeah, because I think that he was asking me about explaining a bit what we were obtaining. No, isn't it, Tarun?
Yeah.
Okay. Perfect.
So before jumping, there is any other question? If not, we can discuss at the end. Yeah, so later.
Okay.
Okay, so I will share my...
Do I have to unshare my screen?
Yeah, you have to unshare.
Yes, you have to share.
And how? Yeah, okay. Perfect.
Okay. Can you now see the screen?
Yes.
Okay. Well, hello, I'm Leire, and as Carlos has said, I will explain the second part of this workshop. This part will not be so technical as the part that Carlos has explained, and I will just explain how we made the taxonomy, the expert-driven taxonomy, and also the persona description of the clusters that we have obtained after processing the datasets. Well, to start, just mention that the datasets that we have used to obtain the 40 clusters that we have obtained were for London, Ireland, Spain, and Portugal. So we also have some differences between countries in our clusters. And also it is important to mention that all the information was made anonymous before using it. And that's why we also need to have to write the persona description of each of the clusters apart from the expert-driven taxonomy. And well, to start, I will explain which were the steps to arrive to the final expert-driven taxonomy. First of all, it is important to understand the heat maps. Now, Carlos has explained, but it is important to spend a bit of time just understanding what they are showing in order to make it easier, the taxonomy and also the persona description. After doing so, first of all, we wrote an orientative persona description just to understand which kind of person was behind each cluster. And while we were doing so, we could see that there were 2 main groups, that were the one of the primary residencies, that was the group with the most of the people, and the group of the others, like second houses, for example. So after seeing that, we started with the easiest part, that was to analyze the group of the non-primary residencies. This part was quite easy and quite visual because the clusters were quite different between each other and they were easy to say what was each one. So we find some street lighting, also some small businesses, secondary houses, like houses that only are used in holiday or weekends, and also some apartments with equipment like energy storage or electric heating. And this part was the easiest part. And after it became the hardest part, that was to make the taxonomy of the primary residences. In this group, there were some clusters that were quite similar to each other, so it was not that easy to separate them in the taxonomy. So the final conclusion was that we thought that the easiest way was to ask those 4 questions that are here mentioned to all the clusters in order to go making the taxonomy. We saw also that not all those 4 questions were need to ask to all the clusters, because in some of them maybe just asking 2 questions you can arrive to the final point of the taxonomy, but in some others you could need to ask the 4 questions. So asking those questions, we make different subgraphs. Here you can see 3 different examples, and you can see that not in all of them there are answered the 4 questions. No, for example, in the first one, we could see that at the weekends they change the behavior and they are not at home all the time. And with this, we could arrive to the final point of the taxonomy. In the second one, instead, we should ask the 4 questions to arrive to the final point. And well, doing so with all the clusters of the principal houses, we finished with the taxonomy. And it is also important to have feedback from another person, because when you spend like a lot of time looking into those heat maps, maybe it can become a bit messy. So maybe another person can see things that you are not able to see. And well, to finish, I will briefly explain the persona description. As I have mentioned before, we need to write the persona description because all the data sets that we are using were anonymized before using them. And with the persona description, what we want is that the description of the real persons and the description that we wrote, that the aim is to be the same or quite similar. We have not tested yet before, so we have not tested this yet. And well, as we mentioned, first of all, we just made an orientative persona description before starting with the taxonomy. We also start with the easiest part, that was the non-primary residencies. Here, for example, in the first one, you can see some accumulation heaters, and in the second one, a summer house, which is only used in July and August. The non-primary residencies persona description was quite easy to do. And after it, we did the primary residency, description of the primary residencies. In those descriptions, it was important to write things more in detail because they were more similar to each other. So in order to make a difference between them, it was important to write the description more in detail. And well, after finishing first of all, the orientative persona description after the taxonomy, it is important to go again to the persona description in order to see if the taxonomy and the first persona description that we wrote were they similar or were saying the same, to see if in the description we were answering all the questions that were used in the taxonomy, in order to have the taxonomy and the persona description linked and saying the same. And with this, we finished this task. So that was all. If you have any other questions, you are welcome. I will try to answer them. And thank you.
So is there any question for Leire or for Carlos?
Can I ask one question? So does the algorithm in the end tell you which household belongs to which cluster, and that's how you plan to do the testing?
Sorry, can you repeat, please?
Yes, please repeat the question.
Does the algorithm then in the end tell you which household belongs to which cluster so that you can test whether the algorithm correctly identified the consumption pattern of that particular household?
Yeah, that's
Carlos,
the aim. No.
No, I mean, I haven't get the point of the question. I mean, so the question is related to the clustering. So
yeah,
you
the
want
question is is the algorithm give you its time series belong to which cluster? And that's where I assume is yes.
yes,
And I think that in fact in one of the collab, I think you show the
yes, I show
know-
the labels of each one of the time series that have been received by the algorithm. So yeah, if you want, I can share the screen again. Let me check. Let me share the screen. Can you see the screen right now? Wait. Can you see the screen?
Yes.
Okay, so here, for example, in the sum algorithm, you can see here each of the files. They are from 1 to 26, the files corresponding to each one of the load profiles. And all those numbers here are indicating which cluster they belong to. So here you can see that file 1 belongs to cluster 1, file 2 belongs to cluster 2, file 3 belongs to cluster 4, and so on. Here, what I have printed is a summary table in which you can see that in cluster 1, there are 13 of those load profiles. In cluster 2, there are 6 of those load profiles, and so on. So yes, the algorithm provides you with a label for each one of your time series.
Thanks.
I expect that this clarifies a bit. Okay, thank you.
The other question that
Yes.
I had was, does the clustering change a lot based on what kind of underlying profile you use? So whether you use the 4-hour profile, the 12-hour profile, or the weekday profile?
So, I mean, you are asking about if the clustering changes depending on different aspects, which are what you said before at the end. So, I mean, the clustering it depends on the inputs that you provide to the cluster. So, if the files, if you put some other files which don't look like the others, the clustering will change.
I'm asking you actually for the results. So for example, you had the real mean 4-hour spring, you had the real mean 4 to 8 spring, or real mean 22.
Okay, I get the point. So if instead of using those features here, you use a different ones. Okay, we have tried with several sets of features. We have computed, in fact, we have computed over 650 features, and we have made a lot of trials with them. And we have arrived to the conclusion that those features here are the best ones to discriminate the clusters. So we have computed different features, not only with the seasonal aggregates. We have been working also with peaks, peak values and off-peak values. And we have also used a series of features known as the catch-22 features that are supposed to be the best features to cluster almost everything, but those features didn't work here. I mean, the cluster 22, the catch-22 features, it's a quite relevant paper that you can find it on internet, which is saying it's selecting 22 features which allows you to clustering any kind of different
and
time
how
series.
did you select these features? I'm assuming not manually, right?
Yes, I mean, the selection of those features has been done manually using the expert knowledge, let's say. Yes.
Using expert, so it was done manually.
So
It was done manually.
Yes.
yes.
Yes. I mean, in Catch-22, there is a methodology to select it automatically, but it's quite complex. Yeah. I mean, we know because we have seen already in several other papers in the state of the art that more or less everyone is reaching to the same point. I mean, it seems like for clustering time series, this is the best way to go. I mean, what they call generalistic what is called features are not working for time series, for electrical time series. So you need to take a specific subset of features. Seems like the one that we are using are the ones that get the best results.
The ones that work the best. Yes.
Okay, thank you.
Okay, thanks. You're welcome. So any other question regarding that part of clustering or feature extraction? So you have the notebook here so that you can try and you can change some parameters. I mean, it's computing a lot of the seasonal aggregates. You can change that part here and try by yourself. Let me check because I'm moving too fast. You can change the features that you are computing here. So you can try by yourself and check what you obtain.
Carlos, can I ask a question?
Yes, of course, Chris.
Well, thank you very much for a very good presentation by both you and by Leire. It was very clear, but for the other people attending, I'm not a data scientist, but I've been involved in most of I've also worked at Goyaner, so I've been involved in most of the research we've done here. And so there was one aspect which I hadn't noticed before when you extend the data series. So when you say, well, we have more than 364 days, but not enough to get to 800 days, we simply copy part of what we have with a shift of 364 days.
Yes.
Will that not introduce seasonal features which are not real, or does it not run the risk of having seasonal features that are not real? For example, you might have been sick in 2018 and in bed for 3 days, and then you copy that to 2017, and then it looks like there's a repetitive event 3 days just around the date when I was sick only 1 year.
Yeah, and what would be the alternative?
Well, discard. Well, no, well, discard. Say sorry. If we don't have 2 years, then we can't use it because we're introducing.
But I mean,
artifacts.
in principle, we consider that the behavior is going to be kept. I mean, for example, it's true that there may be some household in which, okay, you have been sick and you haven't appeared at home for 6 months, but this is just going to happen in just one household. I mean, the general trend is to think that just by extending, in fact, the time series are quite complete, and the extension is just a few weeks or months, and that extension is not going to affect the general behavior of the time series. No. So that's why we are replicating, because we consider that it is not going to affect the general behavior of the household.
Yeah. So and also in this example that you've shown today, we've only worked with 26 time series. Of course, in our real life example, we've worked with tens of thousands, well, with thousands and thousands of
yes, yes, this is something to be clear. We have been working with a data set made by more or less 12,000 time series like those that I have presented today. So today we are working just with a really reduced sample of time series contained in the real data set. Yeah, this is just for as an illustrative example. Thank you for doing that appreciation, please.
Thank you.
Is there any other question? No. If not, I would like to thank Carlos and Leire for the presentation. And also I would like to say that if there is any question, please forward to Carlos and Leire. I don't know if Carlos, if you can put your email address.
Yes, I forgot to put it here. It's true. In the chat. Okay, so
Yeah, put in the chat.
So this is
And
my address.
also, if you will share your screen.
Yeah, I go. So
I can share your screen.
you are also chairman. Okay, so I have left my address.
Let me look if I can find the file that I wanted to show. Well, I can show this one, and that's it. So you are seeing a PDF.
We are seeing a web page. Yes, it's a PDF.
Yeah, yes. Okay, so I wanted to say that the result of what Carlos was saying is going to be presented tomorrow. Yeah.
Yes.
At the parallel session 6, it's this one, just in case you wanted to take a look to the final result with the entire data set. And I wanted also to make a little bit of marketing. So tomorrow we are going to hold a extended version of this session and this another sessions into the Deusto Summer School 2022. So if you wanted to get more and a tutorial with some more tutorial things, not just a webinar, but with forums, with more small pace classes and this kind of things, I invite you to take a look to the Deusto Summer School of 2022. Okay, so if you wanted to get more information about this, just please email Carlos or me, and I will forward more information. So thank you everyone for attending. And it was a pleasure, and see you. I hope I can see you later on into the conference in another session.
Okay.
Thank you.
I'll see you.
Bye.
Bye. I close.
Bye.